going to be one with op amps that's going to be a focus towards looking at a control problem. And what's kind of nice with circuits and control is that they can kind of go one to each other and they kind of interrelate to each other. So one of the interesting ones is thinking about the circuit up here, where I actually have cascaded really two sections, both of which have an R, a C, and a minus R. The minus R is going to give us the instability, and typically if you're saying I've got an unstable pole, this is probably where I'm representing it. Can I actually build negative resistors in practice? Yes. Let's just kind of go with the fact that that's what it looks like. And so you begin with this, and so each of these is going to have the same concept. One is going to be V out, is going to be related V out and V1 minus V out, because I'm going to have V1 here going through R and V out coming back through the minus R term. And then I get what's going through the capacitance. Cool. And so this works out fairly straightforward. I get the same sort of thing, input, V input to V1, and that gives me the minus sign here in front. I expect it to be a minus sign because if you think about it, these are inverting configurations. So nothing terribly surprising here. But the interesting part is that when I look at the canonical form, I'm going to have tau times that derivative equals to minus V1, exactly what I would expect, plus V out. Now the plus V out's a little bit interesting because normally I would have expected a plus V out over here in a nice stable system. For example, if this R was plus and everything's great, but this one really comes across to giving me a minus V out because effectively I've got an unstable pole. Okay. So this makes sense in terms of where we're beginning here, and I've got two of them look identical. Now, one of the things that's super important if you're going to do math along these lines, and I can't emphasize this enough because I've seen this over years and years of different discussions, you really want to, you realize your tau, your time constant is capacitance over conductance, which is an RC time constant, right? G is 1 over R. And so this is your time constant. Well, this is why I've got tau in front of both of these cases. What I want to be able to do, once I get past the nice Laplace structure, is normalize the system. Okay, I know this is going to be proportional in time constant. That time constant's a known value. We have it. We're great. Normalize time with respect to that to T1. And everything gets a lot smoother. In fact, then it would just be an S minus 1 and S minus 1 if you did a Laplace domain. But what's interesting, or T1 here, but what's really interesting then is you say one small shift, basically making minus V1 be my first state variable and V out being my other state variable. I can write a very nice and simple equation, state variable second order equation, which then gives me 3 ones, right? 3 ones here on this side times x. And again, it's not hard to see where those ones would have come from from the original formulations. Again, the minus v helps me get this one out. That becomes minus there. And the minus sign comes through here, which gives me the remaining one there. What's interesting for those who look at such things and have looked at control theory, this is actually the exact set of equations that John Doyle did in his 1978 paper, where he was looking at optimal control theory and margins. So you're like, oh, this is cool. It's actually a really nice system. There's lots discussed about it, and you can actually analyze it. I do want to go through this a little bit because this entire equation set fits this circuit. And yes, you have two, if you look at the eigenvalues of this matrix, yes, indeed, you have two unstable eigenvalues that are both at 1. It turns out both of this is controllable and observable. You can put those together and get those structures out. And all of that works well. And you're like, this is great. And then you think, okay, I should be able to take this one step further and go through the LQR stage, very much like what he would have done. And if I assume that the sensing and actuating cost is equal, and there's also an equal cost across terms. So between between measuring state 1 versus state 2 and so forth. That gives me a Q matrix that's all ones, and an R that's 1 for the typical structure. And so then I get the classical structure in terms of the optimal correction term. Yay, everything is really good here if I solve the Riccati equation. And oh, we love solving Riccati equations. These are lots of fun, right? Okay. The easy way to say it's like, well, we know that from kind of Doyle stuff that, P would be something like this of F. Well, we know that in this case, F is going to effectively be, it's going to be 1 in this case. We can then push through the math and then solve accordingly and then get 2 plus or minus square root of 5. Now, if you want, and 1 and 1. Now, if you want to go a little further, you can say, well, what is P times A in the matrix? You can create that in analytic form. You can say what's B transpose times P, so you know that's going to be P1, 1 and P1, 2, or P2, 2. No problem. The nice thing of this is that PA times A transpose P gives you just sort of the same thing but flipped across the diagonal, so you can just give you a symmetric matrix. Work through the math on these points, and you basically get 3 nice equations. Great. And then you just got to solve it. Solving it's a little bit non-trivial, but one of the things Doyle immediately picks out is it says, hey, P11 and P12 are equal.